So, as always, throughout the night, any questions, please just send them straight to me, either in using the remind code down here or using the chat box on YouTube. Either of those is fine. If you're watching this on the replay, that's great. Fast forward, rewind, all of that is good. So we're going to start with area. We're going to go through some basics of that. And then we're going to talk about volumes of known cross-sections, volumes of revolution. I will tell you guys, I have the most information already on my YouTube channel about this topic. So if you're looking to start from scratch and really go back to square one, I will link down below in the description box all of those videos of things that might be helpful to you. What we're going to do here is hit high points, and then we're going to do a lot of setting up, but not necessarily evaluating, just to get more practice with setting up. As always, any questions, just send them to me. That is the goal. Okay, so area and volume. We're going to start, before we go anywhere, with finding the distance between 2 points, because all of this is going to boil back down to that in the end. When we find area, we're accumulating all those distances, we're summing them up. And when we find volume, we're accumulating the area of cross sections. And those are usually going to rely on the distance between my particular curves. So that's the first thing I want to think about. And I want to think about whether I'm looking at the change in the y values or the change in the x values. So I'm going to look first at AB here. If I want to find the distance between A and B, right, the x values of those coordinates are the same. So I'm going to be subtracting my y values there. And I see that that distance is 3. We can figure that out. But I would be subtracting y values there. If I'm doing CD, again, same thing. That one's longer. But again, I'm subtracting y values. If I'm looking at EF, same thing. I'm subtracting y values. If I'm looking at GH, now we're going this way. When I actually find the difference between those, I'm subtracting x values. And when I look at DF, same thing, I'm subtracting x values. So what I want you to think about when you're trying to decide between a dx and a dy is think about if you were finding that distance, right? Are you looking at the y values being subtracted, so you want the change in x, or vice versa? And that's something we're going to have to think about. So let's start with some of these. And I just want to think about what is the length of AB, okay? So on this first one, AB is the distance from this curve to B, which is on the x-axis. And I see that here I would be subtracting my y values. So knowing that I'm subtracting my y values, this would be 4 minus 1/2 x squared minus the y value of B is just 0. Because remember here, your coordinate here would be x, and then that is really your y value, right? So top minus bottom. If I go to this one, well, now I have going from right to left. Here I'm subtracting the x values. So I see that on this side, x is 4. But on this side, I have y equals x squared. So what I'm going to do is I'm going to solve that for x. So x is the square root of y. And when I find the change in those, I'm going to do the right minus the left. And that's going to be my distance between those. Again, subtracting the x values, which are going to be in terms of y. Okay? This is going to come in really handy as we move on. So let's just do one or two more quickly. So if I look at this one right here, going from G to H, I'm subtracting the y values. This is the y value of one. That is the y value of the other. So I'm going to do top minus bottom. The top is my linear function. The bottom is my quadratic. So that would be the distance between those. I'm subtracting the y values. Those happen to be in terms of x. And let's do one more going the other way. Let's say I want to do this one. So I know that this is y equals x squared. I want to get that in terms of x because I see here that what I would be subtracting are my x values. So square root that, and I'm going to actually have plus or minus the square root of y. The reason I want the plus or minus there is because really this side is the positive square root of y. This side is the negative square root of y. So when I look at the distance between those points, what I'm really doing is positive square root of y minus negative radical y. And you could simplify that, right, 2 radical y, which should make sense if we think about that this distance is radical y, and this is symmetric, so is that one. So that's how I'm getting 2 radical y. Okay, send questions as you have them. That's where we're starting, because that's going to lead us directly into area. So area between curves, what we're always looking at is we're looking at, are we subtracting our y values or our x values? And I want to accumulate the distance between, because what I'm basically saying is the distance between these curves is that, and now I want to accumulate that at every single value between these. And if I do that, that will give me the filled in area. So when I do this, I'm going to pick my upper function and my lower function, and I'm going to say that this is f of x minus g of x. Notice here I'm subtracting my y values, so f of x and g of x are y values. So it's going to be the integral from a to b of those, and this is going to be dx, because I'm looking at each of those being a change in x. Also, this is in terms of x. Also, I'm slicing through the x-axis. All different ways to remember that. Okay? Let's look at another one. Same thing here. My slice goes from f to g, right from a to b, my top function minus my bottom function with respect to x. Okay? It's not going to change as long as we're in the same scenario here. So moral of the story, the area between curves from a to b, integral from a to b of the top minus the bottom dx, right, when we're talking about it going this way. And then I want to look at it going the other direction. So what if I do some of these, right? And actually these are all dx ones. Do I have some dy's? Mrs. G, you didn't put any dy's in here. So let's say I wanted to go this way, between a curve like this and a curve like that. And maybe this is f and this is g. So now when I'm looking at this, I would be finding the difference between my x values, right? So I would want to solve those in terms of y. So let's say that's f of y and that's g of y. So now I would be doing the integral, and let's say that's a and that's b, from a to b of right minus left dy. And again, if you feel like you need more specific practice on this, go back and feel free to look at that video. It'll be in the down bar. We're going to do just a couple examples now because generally this is something we're pretty strong at. So let's look at a couple of these. I'm going to start with this one. And I have h of x is x squared minus 8 and g of x is 3 minus x. And I'm going to think about here the distance between those curves because remember that's what I want to accumulate. So I'm going to do top minus bottom subtracting my y values. So the distance between those curves is the linear function, which is g, so 3 minus x, minus the quadratic function, which is x squared minus 8. Since these are in terms of x, I'm going to have dx there. And so now what I need to think about are my bounds. I need to find the intersection of those. In a non-calculator section, you would just set them equal. This one I can tell you is a calculator active. So let's actually look at these graphs. So that's what these graphs looks like. So one of my intersections is at negative 3.85. The other is at positive 2.85. So I'm going to integrate from negative 3.85 to positive 2.85 because those are my intersection points here and here. And again, because we're moving along the x-axis, we're looking at dx. I'm using x values there. Now you could also write this as g of x minus h of x. I would highly encourage that, especially on a calculator active section, because then you don't miscopy something, right? Okay, let's look at another one. So this one says f is x squared and g is cos x. Find the area between the two curves. So same idea here. I'm doing top minus bottom. The top function is cos x. The bottom function is x squared, and I'm subtracting the y values. So that is g minus f. Because these are in terms of x, this is going to be dx. And let's think about these bounds. Again, non-calculator section, you could just set this equal. I am going to look at the graph because this one would need to be calculator active. So we're going from negative 0.824 to positive 0.824. So negative 0.824 to positive 0.824. And that would be my area. Now, they could pull a fast one on you here, and I just want to talk about why really quickly. Because this region is symmetric over the y-axis, right? It's two even functions. So this region over here is equal to that region over there. So this could also be written as the integral from 0 to 0.824 of g minus f with dx at the end, of course. And then I could double that, right? That would still be the same because what I would be saying there is take the region from 0 to that value and then double it. So just know that, especially on a multiple choice, it can look different but be the same exact thing. Okay, let's do another one. Let's try this one. So this one says I've got y equals x, square root of 1 minus x squared, and y equals 1/2 x. Again, on a non-calculator section, you would set those equal, solve for the 3 points of intersection. I can see pretty clearly here that this is one of them. And the other two I'm going to get from my graphing calculator. So looking at this, these are my curves. So I'm going to just quickly do an intersection. So the first intersection is at negative 0.866. So I'm going to write that down. Negative 0.866. The second intersection, let's get that. I'm going to guess that it's symmetric, but let's prove it. Let's never assume that. We're going to do the intersection coming over here to there. And yeah, it is at positive 0.866. So that's 0.866. Now here's the deal with this. We have two distinct sections. So when I do this, I'm actually going to need to use two integrals. The first integral is going to go from negative 0.866 to 0. And I need to, again, do top minus bottom. That was not a good highlighter. So your top there is 1/2 x. And then the bottom is x radical 1 minus x squared dx. So that's the area of this first region. Now I'm going to switch to another color and I'm going to do this second region. So the second region is going to be plus the integral from 0 to 0.866 of, now they reverse. So my top function now is x radical 1 minus x squared. My bottom function is 1/2 x dx. So when I want the area of something with two distinct sections, normally that means I'm finding two distinct areas. Okay. Please send questions if you have them. I'm going to draw us one more because I want to be able to do one of these problems. So let's say I want to find the area between x equals y squared and y equals x minus 4. Okay, so x equals y squared is going to look like that. Y equals x minus 4 is going to cross at negative 4 and go up like that. So now we need to think about this a little bit more carefully. Because if I try to do top minus bottom here, look what happens. I get top, I get bottom. So there, top and bottom are the same curve. Here, top and bottom are different curves. So you would actually need to break this up into two distinct sections if you did that. So what I would do here is instead of trying to go this way and having to break it up, I would try going the other way. Because if I go the other way, there is one function consistently to the right and one relation consistently to the left. And so I can do right minus left. Notice that now I'm subtracting the x values. These should be in terms of y. So this would be x equals y plus 4. And this would be y equals square root x. And so what I'm doing is I'm finding my integral from the line to that. So from y plus 4 to square root x, x equals y squared is already in terms of y squared, and dy, because I'm doing this in terms of y. And then what I need there are my y values. So what I would do is I would plug this into my graphing calculator, and I would look at those y values. I'm going to assume you guys can do this, but again, you would just throw these into your graphing calculator. So my first one was y squared, so I can do square root x and negative square root x. So there's positive square root x. Here is negative square root x. So that gives me x equals y squared. And then I can do y equals x minus 4. And I would just find the intersections there. And I would want to pick my y values. So, actually doing this, finding my integral, or not my integral, sorry. I hit integral again, intersection. I'm going to go from, the line's not popping up. All right, this is being funky. So you would graph these, see where they intersect, and then use those y values. So from your lower y to your upper y. Okay, if you have questions about area, please send them, because what we're going on to next is volume. And this is normally where I see the most trouble, not because it's crazy hard, just because it's a little bit hard to conceptualize. So again, if you have questions, send them, but we're going to move on to volume until I hear from you. So, calculating volume by summing up areas. Here's what I want you guys to think of. And I'll do this like what I did last time. I'm not going to get all the foam out, but think about this. If this is my shape, right? This is a rectangular prism kind of looking thing. What I'm looking at here is a stack of, in this case, papers, right? And each piece of paper is one layer in that stack. When I layer them all up, I get the volume. And so the reason that volume is the accumulation of area is the same reason that volume is area of the base times the height. Your area of the base is this, and then you're stacking all of those up, and it gives you your volume. So this is really key here, okay? Think of the volume of a stack of paper. If you calculate the area of one piece of paper, and then multiply it by the thickness of the paper to get the volume, and add all those up, you will get the volume of the stack. That's what we're doing. So what I'm saying is anytime I'm finding volume, I'm accumulating the areas. So the challenge normally is coming up with a formula for your area. That's normally where we get stuck. So we're going to look at a couple where it's just a basic scenario, and then we're going to build on that from there. Now this was a failed test question. You guys almost got this on a test, Elmo cake and all. But it illustrates the point pretty well, which is good. So Mrs. G volunteered to bake a cake for her 3-year-old niece's birthday party. This was probably a mistake. Despite her calculus prowess and her fantasy football expertise, she isn't a baker. She spilled a bunch of batter and lost some of the decorations, and Elmo's looking a bit frazzled. Family is trying to figure out if there's still enough cake to feed everyone since it's irregular. Mrs. G figured the only logical answer was to write a function to represent the area at any given height. So this is thinking about taking Elmo, slicing him this way, and I would get the area of his cross-section. So this is kind of strange, but think about if this was your cake. This is a turtle. You slice it, and at any given point, that would give you the area of the cross-section. That's what this formula is giving you. So this is your cross-sectional area. Height is in centimeters, and A is area in centimeters squared. So write an integral expression. Hint on the AP exam. If it says that, you better have an integral. To represent the volume of the cake if you know it is 25 centimeters tall. So here's what I'm talking about. I'm talking about taking cross-sections of Elmo and stacking him up until he is 25 centimeters tall. Almost think about trying to 3D print something, right? You have a layer, you layer on top, you layer on top, you layer on top. So what I would be doing is I would be integrating from 0 centimeters tall to 25 centimeters tall, my area function. Okay, so write an integral expression to represent the volume of the cake. So now it says if each person eats a 16 centimeter square piece of cake, is there enough to feed the party of 30? So here's what I would think about. Each person is eating 16, right? So what I would do is 16 times 30, which, again, if you have a calculator, throw it in there. If you don't, do 16 times 3, multiply it by 10. So 16 times 30 is 480. So this is how much we need. Is there enough to feed the whole group? So I'm going to calculate this integral. So I'm just throwing this into my calculator, math 9, 0 to 25 of 3x plus 15 times the square root of x squared plus 10x plus 25 dx. So I threw that in my calculator. That gives me 2,6,8,7,5. Is there still enough cake? Yes, there's still enough cake. Okay, that's my amount of cake. Okay, cool. All right, next one. These are both from the last 2 years AP exams. This is how they've asked volume on the last 2 years AP exams. So if you understand that idea of summing up area, then you're going to be fine on these. So this one we're really going to focus in on C here. So a tank has a height of 10. The area of the horizontal cross-section is given by this table. And then in part C, it says the area of a horizontal cross-section at height h is modeled by this function. So this is an area function. Based on this model, find the volume of the tank, indicate units of measure. So what I would be doing I would be saying, let's take that area function and let's integrate it from 0 to the height. And they told us that this is 10 feet tall. So 0 to 10 dh. So that would be what I would be starting with. I would plug that into my calculator. And I want to think about my units. This is in square feet. So this would be in cubic feet. So what I would do is just throw that integral into my calculator, and that would give me my total volume. Right? They gave me the area formula, so I'm integrating to find the volume. Okay, next one. This was like the question heard around the world. This blew people's minds because they thought it was a cone. If they don't say cone, assume it's not. So here's what they said. The inside of a funnel with a height of 10 inches has circular cross-sections, as shown. The radius is given by this. So I don't have a formula for area here. I have a formula for radius. So find the average value of the radius, use the average value formula. Part B was where we got really stuck on this here. Find the volume of the funnel. So what I want to think about is summing up the areas. They told me that I have circular cross-sections, and I know that the area of a circle is pi r squared. So, knowing that I have a formula for area, or for radius, sorry, it's going to be pi times 1 over 20, 3 plus h squared, That's going to be my formula for area. So to find the volume of this, I'm going to integrate from 0 to 10, because 10 is my height, of pi times my radius, which is 1 over 20, 3 plus h squared dh. And again, we can evaluate that. I'm much more worried about the setup tonight. Again, take your cross sections, sum them up. Okay, so what that leads us into is finding volumes with known cross sections. And so to do this, I'm going to sketch my solid if I can, and I'm going to find a formula for the area, and then I'm going to integrate it, because that's really my goal here. So let's start with this one. The base of a solid of the region enclosed by this semicircle and the x-axis, cross sections perpendicular to the x-axis are squares. So here's what I'm going to start with. Perpendicular to the x-axis means they're coming down like this. So think about that distance. This distance is the change in y values. So I'm going to do the top y value, which is 25 minus x squared, minus the bottom y value, which is 0. So that's what that distance is, just like we did in area. Now I'm thinking about taking three-dimensional squares and setting them on top of this. So I'm thinking about taking a square here and like setting it coming out three-dimensionally. Same thing here. Coming out three-dimensionally, same thing here. Coming out three-dimensionally. And so I'm setting these on top of it. So if this is my region, I'm setting them this way with that as my base, right? Not going through the plane, but really with that as my base. So the area of this is going to be the area of a square. My side length is that, which is this formula that I found before. So my side length is the square root of 25 minus x squared minus 0, right? My bottom is 0 squared. And so that's my function for area. So what I'm going to do now here is integrate that. So I'm going to say, okay, do the integral of the area function squared, because it's area of a square, dx. And I need to do this from this x value to that x value, which is negative 5 to positive 5. That would be a pretty likely candidate of one you'd need to do by hand. Now, they could get mean again. And in a multiple choice, they could say something like this: the integral from 2 times the integral from 0 to 5 of the square root of 25 minus x squared dx. So look for that symmetry. If you see something that's symmetric, look for that symmetry. All right, let's do another one. Please send questions as you have them. Base of a solid is enclosed by y equals negative x squared over 4, or over 9 plus 4, and y equals 0. Cross sections perpendicular to the x-axis are rectangles where the height is twice the length of the side in the plane. So think about this. I have a rectangle, and actually I'm going to do this going this way. This is going to be my side in the plane, so that's, let's say, S. The height is going to be twice that length. So the area of this is going to be 2s squared. So let's think about what S is. We know that these are perpendicular to the x-axis, so same idea. So I'm going to do top minus bottom for this. So this is going to be S equals negative x squared over 9 plus 4 minus 0. The bottom is 0. So my area function is 2 times negative x squared over 9 plus 4 squared. So to find my volume here, I'm going to integrate that, so plug that in there, to the integral of negative x squared over 9 plus 4 squared dx. And I'm going to go from here to here. And again, they could get you a symmetry. I'm going from negative 6 to positive 6, but they could go double negative 6 to 0 or double 0 to 6. Okay, let's grab one more of these. Actually, we're going to do, let's do this one. So base of a solid in a region is the region bounded by y equals x squared and y equals 4. So I'm going to graph these. So y equals x squared and y equals 4. I would expect you to be able to graph those, right? Parent functions. The solid lies between planes perpendicular to the x-axis, at x equals negative 2 and x equals 2. So we're going this way. So again, I'm subtracting my y values there. So that length would be 4 minus x squared. And it says cross sections to the y-axis, or I'm sorry, cross sections perpendicular to the y-axis. I misread that. Cross sections perpendicular to the y-axis are squares. So perpendicular to the y-axis means we're going this way. So now I'm subtracting my x values, not my y values, okay? I'm subtracting my x values. So what I need to do is get these solved for x, or in terms of y. So if this is y equals x squared, then what I need to think about is that x is plus or minus the square root of y. The right side is the positive square root of y. The left side is the negative square root of y. And so the distance between these, that side length, is the square root of y minus the negative square root of y, which is 2 radical y. Same rationale we used before on the area. If this piece is radical y, so is that. Of course there are 2 of them. So now I'm integrating. And when I integrate, because I'm going this way, I'm going to use my y value. So I'm going 0 to 4 of area of a square is side squared, which is 2 radical y squared. So I'm integrating that, dy. Again, we're setting up, we're not really solving. Questions? Okay, again, if you want more practice on this, look in the down bar. I've got a whole video just on volumes of known cross-sections. It's all about finding that area formula and then just integrating. All right, last thing, let's get into some volumes of revolution. And I'm going to tell you guys this. Again, copious amounts of videos in the down bar on this. But if you're struggling with this, here's what I would do. I would treat every question like it's a washer. And your inner radius may just happen to be 0. So to find the radius, you're either going to do top minus bottom or right minus left. If you're struggling, if you get washers versus discs, go for it. But if you're struggling, treat everything like a washer. And we'll let the inner radius equal 0 if it's a disc, right? There is no other inner radius. So let me show you an example of what I mean by that. Let's say I'm looking at this graph right here. Now, this is a washer. It's a solid revolution, right? So I could say that my outer radius is from there to there. So let's say this is f of x. My outer radius would be f of x minus 8, because that's 8. My inner radius, well, there really isn't one, right? It's solid. So this would be 8 minus 8. So my inner radius would be 0. And you could still treat this just like a washer. Okay, same thing on this one. So let's say again that this is f of x. So my outer radius is f minus 8. My inner radius would just be 8 minus 8, which is 0. So if that helps you to think about these, treat everything like a washer. Unlike one like this, where maybe this is f and this is g. So my outer radius would be f minus 8. And my inner radius would be g minus 8. So that's something you can think about. And if you're struggling with washer versus disc, treat everything like a washer. And if the inner radius is 0, so be it. Then it's just a disc. Okay? So let's look at this one. R is the region enclosed in the graph of this. And the horizontal line y equals 4. And you can't see that. There we go. So we want to find A, the volume generated when R is rotated around y equals -2. B, the base of the solid if this is an isosceles triangle. And C, I want to find a value of k, right? But do not solve an integral expression to find a value of k that divides it into 2 equal areas. So let's start with A. Let's start with A. So on A, it says to rotate around y equals -2. Now, I'm going to tell you guys this was calculator active. I would find these intersections. This is at 0, and this is at 2.3. So that's what I'm worried about, okay? Put those in, see where they intersect. I want to go around y equals -2, so that's going to be down here. So when I rotate this is going to be a little hard to visualize. Your outer function will come around that, like this, and it would make like a cylinder because we're rotating a straight line. The inner function is going to also rotate through, but you're going to have kind of different size radii here. So this is going to come like this, and then up, and then back down. Again, not totally accurate, but could be worse. So this is definitely a washer. We've got a hollow in the middle. So here's what we're going to do. We are going to say, treat everything like a washer if you're unsure. The outer radius is from here to there. So my outer radius, I'm going to zoom in a little bit and move this over. My outer radius is from 4 to -2, top minus bottom. My inner radius is from here to here, right? Here to there, that function down. And that's from F to -2. So this is my outer radius. This is my inner radius. So when I set this up, I'm going to say part A is the integral from 0 to 2.3 of your outer radius pi times your outer radius squared, which is 4 minus -2 squared, minus your inner radius squared, which is F minus -2 squared dx. And again, on the actual AP, I would evaluate this. I would just put it in my calculator. Again, treat it like a washer. This one happened to be. Okay, part B says that now this region R is the base of a solid, and we are putting right isosceles triangles with a leg as the base. So what I'm doing is I'm just putting a leg of a triangle here. It's a right triangle, so it's coming up like that, and this is in 3D, so this is hard to see, and then it comes down over like that. So again, right triangle coming up from here, going down and going over. So this has right triangles sitting on it. Area of a triangle is 1/2 base times height. And if I know it's isosceles, I know it's 1/2 base squared. So I need to figure out the length of the base. This is the length of the base, right? That distance. So the length of the base is top minus bottom. So your area function here is 1/2 top minus bottom squared. So for part B, this is A, let's do B. For B, I would be doing the integral from 0 to 2.3 of the area of that triangle, 1/2 4 minus f of x squared dx. And again, throw it in your calculator and you're done. All right, last part is part C, and part C is really the critical thinking part here. So there is a vertical line K, x equals K, that divides this into two regions, right? But do not solve an equation to show where the areas would be equal. So here's what I would think about. I want the area of one side to be equal to the area on the other. So what I'm basically saying is the area here from 0 to K should be the same as the area from K to 2.3. So here's what I would say for C, and there's more than one right answer here, but here's what I would say. I would say that I would want the integral from 0 to K of 4 minus f to be equal to the integral from K to 2.3 of 4 minus f dx. And that's all you need to do, right? Set up some kind of an equation that helps you find where K would be. It doesn't say to figure out what K is. Just set up an equation. I've seen some people in the past who did the integral from 0 to K minus the integral from K to 2.3 equals 0. I've had people do the integral from 0 to K plus the integral from K to 2.3 equals the integral from 0 to 2.3. So there's been lots of different ways. They're all good as long as it will figure out where K is. So these were your actual scoring guidelines for this. These were your scoring guidelines. Part 1 was 4 points. Integrand was 2. So treating this like a washer and having this and then that was 2 points. Your limits from 0 to 2.3 was a point, and the final answer was a point, and it was just on your calculator. Part B was 3 points. You needed the integrand, so you needed 4 minus f of x, and you needed 1/2 the base squared, and then your answer was 1. And part C, again, that's one example, but there are many. So area of one region needed to be correct, and then the equation needed to be there. All right, keep sending questions if you have them. We are going to do just a couple more, and then we're done, and all we're doing on this is setting it up, okay? So on this one, we're going to let R be the region in the first quadrant and close by these graphs, 4 radical x and 2x. I'm going to label this 2x and 4 radical x because I would like to know what I'm dealing with. If you want to be like extra lazy with what you're writing, you could also say let y equal 4 radical x equal, so yeah, what you could say is let f of x equal y equals 4 minus radical x, or 4 radical x. Or even simpler, you could leave out the y. So you could say let f of x equal 4 radical x and g of x equal 2x, and then you wouldn't have to write it every time. But I'm going to use those here just because that's what they gave me. You cannot just say f and g unless you define it, because they didn't give it in the problem. So first thing I need to do is I need to figure out where they meet. So this is at 0. This looks like it might be at 4. Let's confirm that. Let's set these equal to each other. So 4 radical x equals 2x. I'm going to square both sides. So that would give me 16x equals 4x squared. I'm going to subtract that over, so I would get 4x squared minus 16x equals 0. And take out a 4x, and that would give me x minus 4. So my intersection points are definitely at 0 and 4. So this is going to be the integral from 0 to 4. And when I do area, I want to do top minus bottom. So 4 radical x minus 2x dx. And again, I'm assuming that you guys can integrate it. I'm not going to do that. I want to focus on the concept here. All right, part B, the region is the base of a solid. For this, at each region, the cross-section perpendicular to the x-axis has this area. So it's giving you the area formula. So find the volume of the solid. So all I'm going to do is I'm going to say, okay, let me accumulate from 0 to 4 A of x. They told me what the area is. I don't need a special formula for it. Okay, next one. Another solid has the same one. I'm going to change this to semicircles because we've done a lot of squares. So let's do a semicircle. So, perpendicular to the x-axis are semicircles, right, but do not evaluate an integral expression for the volume of this solid. So, I know that my side length here is this distance. I'm putting semicircles here. So here, S is going to be 4 radical x minus 2x. The area of a semicircle is pi r squared over 2. And this, notice, is the diameter of that semicircle, right? So if I want to actually put my radius in, r is going to be 4 radical x minus 2x over 2. Or you could simplify that and make it 2 radical x minus x. So your area function is 1/2 pi r squared. And so this is going to be the integral from 0 to 4 of 1/2 pi r squared dx. All right, yet another one perpendicular to the y-axis. The base of your solids are squares. So let's think about going with the y-axis. So it looks like this. Going perp to the y-axis, I can do right minus left. I just need these in terms of y. So if y equals 2x, then x equals y over 2. And if y equals 4 radical x, then x equals y over 4 squared. So this is going to be the integral of right minus left squared, because the area of a square is pi r squared, or is just side squared, sorry. Squared, dy. And your bounds need to be y values now. So this is still 0, and this is at 8. Your y value there is at 8. Okay, let's do some revolutions. Right, but do not evaluate an expression that gives this when rotated around the x-axis. If you're in doubt, use everything as a washer. So I'm going around the x-axis. This one happens to be a washer. It's going to look kind of like that. We're going to have a gap in the middle. So remember, washers are pi r squared minus pi r squared. You guys can't even see that. So let's think about our outer and our inner radius. My outer radius is from this function to the x-axis. So my outer radius is 4 radical x minus 0. My inner radius is from here down to the x-axis. So that is 2x minus 0. So this integral would be the integral from 0 to 4 of pi times your outer radius squared minus your inner radius squared. And you don't need the minus zeros, but I'm leaving them there. All right, the next one, we want to go around the line y equals 8. We want to go around the line y equals 8. So let's do that. I'm going to erase this. Y equals 8 is up here. And I'm going this way. So now I'm going up. And it's going to look more like a cone on the outside. And then have this like almost like inflated sidewall, right? So let's think outer radius and inner radius. Your outer radius is this. So that is 8 minus 2x. Your inner radius is this, which is 8 minus 4 radical x. So what I want to do here is integrate from 0 to 4 pi my outer radius squared minus my inner radius squared dx. All right, last one, and then I am just going to stick around for questions. Write but do not evaluate an expression that gives a volume when this is revolved around x equals negative 1. So, x equals negative 1, we're talking over here. We're talking about going around this way. So what I'm talking about is now using dy. So, I can already tell you that this is going to be pi, the integral from 0 to 8, dy. And I need to get my outer and my inner radius. So again, I'm going to rewrite these in terms of y. So x equals y over 2, and x equals y over 4 squared. So outer radius, your outermost radius from the axis of revolution to there is y over 2 minus negative 1. Your inner radius from here to the axis of revolution is y over 4 squared minus negative 1. And let's just sub those in. So outer radius squared, which is y over 2 minus negative 1 squared, minus inner radius squared, which is y over 4 squared minus negative 1 squared. So again, treat everything as a washer if discs are throwing you off, the difference between them, because your inner radius will just be 0. Okay, I'm going to hang out for a couple minutes, see if you guys have any questions.